Hello, good afternoon. Let me show you how you can work with the stiffnesses from IDEA StatiCa connection in the global software, and let me show you the comparison with material nonlinear analysis in the application IDEA StatiCa Member, which consider also all the stiffnesses of the connections which are here. So we will start with the application IDEA StatiCa Member. Mm, at this application, you can see it's a typical frame. The height is 4 meter, the length 10, uh, the load there is 10 kilonewton per meter. Um, Split it to the width, 280 millimeters. So this is our model. These are our frame corners, which are stiffened, and in the middle there is a connection, which is bolted and welded also. So in the first stage, I will run the analysis and show you the results. So in the results, we can display the internal forces. So from the trend of the internal forces, we can see that everything is correct, but right now we are interested in about the numbers. So here is 70.5 and 49.4 kilonewton meter. You can see here is some drop close to the connection part. So this is our internal forces, mainly the bending moments. And let's check the total deformation. This is the sum of all the vectors of the deformations. So you can see if I turn off the internal forces, and yeah, you can see 8.3 millimeters in the middle. So I can scale up the deformation, and you can see how it's deformed. And this is my deformation. And right now we can jump to the IDEA StatCa connection and investigate the stiffness of this part. So this is my connection in the IDEA StatCa connection, where I put the bending moment only, and this is my analyzed member. The analyzed member is member B2, which has theoretical length 5 meters right now. So I've calculated the stiffness analysis, so we can immediately check the results and see what we get. You can see this is the nonlinear trend of the rotational stiffnesses. So it's on the vertical axis there is a bending moment, on the horizontal axis there is a rotation in the milliradian. So here is very detailed explained the stiffnesses, like the initial one and the second one. The second, this is the stiffness which we'll be using, because this is the stiffness for my bending moment 49 kilonewton meter, and my rotation 2.4 milliradian. You can see the classification of the joint is semi-rigid, so we should take into account the stiffnesses. We will take into account 20.3 meganewton meter per radian, and I would like to show you how you can put this linear stiffness only one number, and how you can, let's say, input all the nonlinear trend of the nonlinear trend of the curve. If you would like to, let's say, export the curve, you can export it to the CSV, where you will get this rotation and the bending moment, and you can see that this is a completely non-linear trend, and this curve will be inputted to your global FEA. So we can compare two solutions, one solution with only one stiffness, and the second solution with this non-linear trend, which will be inputted to global FEA. I selected for design Midas Civil. Mm, so you can see it's the same model, but there are um, two main differences. In the first model, there is a beam and release function that is at this point, and it represents um, the rotational stiffness 20.3 meganewton meter per radian. If I jump in to the tab, you can see that this is my value, but do not forget that this is in the kilonewton meter. So it's 20,300 kilonewton meter per radian. The second function, which is related here, is in the part of the elastic link where I'm connecting, let's say, two nodes, and my function is completely non-linear. This is the trend which is symmetrical on the both sides, and these numbers are taken from the CSV spreadsheet. So let's run the analysis to see the results. I will run it. I'm getting the results, and in the results we can see at first the deformation. So I would like to see the total deformation and check the results. So at first we can check the value which is in the middle. It's 8.3, so this is exactly the same value which we can find here. So the stiffness is really good correlation. And if we check it for a second model where is the nonlinear spring, so we can see that yeah, the value is 8.11. So this is also very good correlation. Right now we can see the bending moments, and from the point of view of the bending moments, we can see the results. So let's check the bending moment in the middle. So in the middle we can see that there is a 42, approximately 42 kilonewton meter, and the member is showing some drop close to the area of the joint. So if I don't want to see only the extreme but the section, so close to the area of the connection, you can see I'm about 45. So this is also very good correlation with the bending moments for linear stiffness here, and for the nonlinear we can see approximately 42 kilonewton meter. This is very important also to check the bending moment in the area close to the frame corner. So if I check it here, I have a 70.5, and in my calculation I have 73.8. So this is this value, and this is for linear spring, and for non-linear spring I have 72.8. So you can see the values are exactly the same, let's say 95% comparison. So do not hesitate and use the IDEA StatCa for your stiffness calculation and correct evaluation of the results. So thank you for your attention.